Today, we are moving from univariate and bivariate statistics, so statistics of one or two variables, to multivariate statistics, where we deal with a dependent variable and two or more independent variables. And specifically, we deal with the most important and at the same time the simplest multivariate method, the multiple regression. Put simply, multiple regression is a natural extension of simple regression to a situation where more than one independent variable is included. Now, including more than one independent variable is potentially extremely useful, as it enables us to study the effect of one independent variable we are interested in on the dependent variable, while controlling for effects other variables might possibly have on our dependent variable. In other words, we are trying to explain the effect of some causal factor we study on some outcome variable or dependent variable. And in multiple regression, we can do this better than in any bivariate technique, such as simple regression, because here we can control the effect of everything else that might be also relevant, but that we do not want to focus on in our specific analysis. Now, this is super cool, as it enables us to almost replicate the logic of experimental research design. We study the causal effect of A on the outcome variable B, while controlling for the effects any C or D or whatever could have on B, thus parsing out the pure effect of A. Now we will first do the whole thing in R, and then we will have a quick look at Excel. So let us load the dataset of staff in international organizations, this time the one with dot used as a decimal separator. And let us again create our logarithms of the three important variables. So number of staff, size of economy as measured as GNI, or gross national income, and population size. Now before we jump into multiple regression as such, we can check how a nice 3D plot plotting these three variables can be created. The library called scatterplot 3D is necessary for that. So install it and load it. And since I already have it installed, I just load it with the command library. Now the plot is created with a command of the same name, so scatterplot 3D. In brackets then, this is followed first by the two independent variables, so log population, log GNI, and then the dependent variable. All of them separated by commas. So the dependent variable is the variable that should be plotted on the vertical y-axis. So let us try it. And here we are. Now, you may note that while doing this, while preparing the graph, I've created an object called Amazing 3D Scatter. And this object contains all the information from which this graph is actually created. We will use it later on as well. Now, if we want, we can give the graph some facelift by giving it, for example, a title, using the option main, by labeling its axis, or by changing the type of depiction of the data points. We can also change the color and the shape of the dots or the data points. Just Google something like graphical parameters R and plot to get to some website that describes all these possible options that can make your graph look cooler. So let us do this now. And here we are. So you can play with the options if you want, but this is perhaps something for long winter nights rather than for a short video. Now, one really cool thing although perhaps more aesthetic than practical, is to plot through the data in the three-dimensional space we have a regression plane. And to do that, we will first need to tell R to do the regression analysis, as only on the basis of the analysis as such can R actually form the predictions of the values on the dependent variable y. Then it will use these predictions, the y-hat values, as one component of the coordinates that will form the plane. The combinations of all the values of the two independent variables will then form the other two coordinates. So each individual point that will form the regression plane, and there will be thousands and thousands of them, will then be given by these three coordinates, like x, y, and z coordinates in any 3D high school graph. Now to get R to calculate the regression plane, we will use the command lm for linear model. In brackets, we specify first the dependent variable, and then separated by a tilde, the two independent variables, which are separated by the plus sign, or rather connected by the plus sign. In our case, we are explaining the values of the number of people from a country in international organization secretariat, so staff, in logarithm. And we are explaining this variable by looking at the country's population size and economy size. Again, both of them in logarithms because they are both very heavily right skewed, so we are taking a logarithm to make them appear more normally distributed. And we are again indicating the data source with the option data. So now we had R calculate the regression, and we have an object which I've called cool plane. You can call it whatever you want. You can see that it's stored here, some kind of object. And this object contains the results of the regression calculation of the estimation. Now to plot the plane over the data in the 3D graph, we can use the command plane 3D, which is attached to the 3D graph we have already created. So you may remember that I labeled the three-dimensional graph amazing 3D scatter right here. So now I will attach it to the plane by joining the two with a $sign. Finally, in brackets, we'll insert the name of the plane object we have just created, which is called cool plane. Now do not get confused here about the $sign. We are not really dealing here with variables and data sets. Just take it as a fact that this is the command that tells R how to plot the plane over the data. It looks so because someone has programmed it to look so, not because there would be some obvious reason for this. So, good. We have a regression plane plotted over the three-dimensional graph. And the shape of the plane, or rather these angles, indicate the slopes of the two independent variables. And remember that technically speaking, this is almost the same as the regression line plotted over a scatter plot we saw earlier in the course in 2 dimensions. Just this time we are in 3D rather than 2D. This is the only difference. So now we can go to the regression analysis as such. And almost exactly as last time, we will see that in fact we already have everything ready for it. So to perform the regression analysis, we need the command lm, which we have just used, and then again, first the dependent variable, and then separated by a tilde, the two independent variables. So for instance, first the log of population, then a plus sign, the log of gross national income. And again, one option indicating the data source so that we don't have to use the $sign for each of these variables individually. Now we can create an object called my beautiful model 2, because we had my beautiful model last time. So let's have number 2 today. So let us create this object. And if we then ask R to summarize the result of the estimation, we get our regression or multiple regression output. So we have the results about the slope coefficient for each of the variables and the intercept here. We also have the standard errors, again for the intercept on the first line and for each of these independent variables, so the standard errors of the slope. And we have their associated t-values, so the t-statistics. And importantly, we also get the estimates of the probability, again for each of these components individually, that any of these estimates is in fact 0. And you see that these probabilities are extremely low here. So very close to 0. The probability that any of these numbers is in fact 0, given that there is some uncertainty involved in the estimate, which is captured by the standard error, is very low. So the probability, there is no relationship between each of these independent variables and the dependent variable of log staff n is extremely small. Now the only difference from simple regression really is that there are more independent variables here, not just one. One small difference is that in multiple regression we tend to report the so-called adjusted R-squared rather than just multiple R-squared or R-squared. In fact, quite often we report both of them because they are quite useful. Remember that R-squared tells us, this R-squared, tells us what share of variation in the dependent variable is explained by our model. In this case, by our model with two independent variables. The reason we often report adjusted R-squared is that adjusted R-squared is what it says it is. It is adjusted. It is adjusted for the number of independent variables contained in the analysis. So it punishes you if you would have the stupid idea to try to plug into the analysis as many independent variables as possible. Instead, adjusted R-squared kind of pushes you into what you should indeed do anyway. That is, think carefully about a limited number of theoretically potentially important factors, independent variables, that could have an effect on the dependent variable, and that should be controlled for in your analysis. So while multiple R-squared has this beautiful interpretation that it's the percentage share of variation explained, variation in the dependent variable explained by our model, adjusted R-squared doesn't have this simple, nice interpretation, but it's very useful in that it gives us an adjusted measure of multiple R-squared. Now, this brings us to one important point, namely to that in order for all this regression stuff to make any sense, a couple of assumptions needs to hold. So let us see in the next video how to check that. So how to run what is called regression diagnostics.